And so the title of 8.4 is the Divergence and Integral Test. It's about a couple of tests. But before we get into these specifics, I want to help us wrap our mind around what we're doing. And so we are considering series like summation as k goes from 1 to infinity of sum a sub k. Again, this is an infinite sum of terms, a sub 1, a sub 2, a sub 3, etc. And so our big question that we're regularly going to be asking ourselves, so there's a question about, did we finish 8.3 last week? Pretty close. Yes, it finished with the geometric series, and then they did some extra examples. So yeah, 8.3 was finished. 8.7 was the formula for the geometric series, which we covered. And then that was the last thing they did in the section. So yeah, 8.4 is covered. Let me see if I can put that up here. Okay, so the big thing we're going to consider now is we're looking at a series and we ask ourselves, it converges or diverges? And as I mentioned before, sometimes if a series converges, you're able to find out what value it converges to. And our perfect example is like the geometric series, where we have a little formula. But that actually moving forward at this point, we're usually not going to be able to figure out or try to figure out what a series converges to. There's a little thing in here where they kind of help you zoom in on that with the thing about a remainder that I'm actually going to kind of gloss over or skip over. Because in the modern world, if a series is known to converge, then you can simply use a numerical process like putting in a very large k value and then see where it converges to. So our main goal is that we're going to have converge or diverge problems where you're only answering whether it converges or diverges, not worrying about if it converges, where it does converge to. So let's look at a starting example. So consider let's say I did, how about this? A series as k goes from 1 to infinity of 0.6 times 10 to the minus k. Okay, so what does this look like? When k is a 1, we have 0.6 times 1/10. Actually, I'll just make that a 6. I apologize, a short adjustment here. Let's just make this a 6 because it looks simpler and comes out a little nicer. So there we go. So we have 6 times 1/10 plus 6 times 10 to the minus 2 would be 1/100th, etc. And if I wrote this as a decimal, you could see this is 6/10 plus 6/100ths, or 0.6 plus 0.06, etc. So I wanted to do something where even in series notation, it looks a little uncomfortable, but really we could recognize this pretty quickly. So this is an example of an infinite series because it's an infinite summation of terms. We could recognize that I'm adding 0.6 and then 0.06 and then 0.006, so that I could write this as 0.6 with a bar over the top. And that's 2/3. So this is an example of a series that converges simply because we can sort of do the addition decimally and see that we just get a repeated 0.6 decimal that goes on forever. And maybe we recognize that that's the same as 2/3. Now, how would you recognize that? At this point, that's actually done using infinite geometric series. So I'll do that next. But maybe on your calculator, you've just seen that enough times to believe that and convince yourself. Okay, so this is the situation in. We're given an infinite series, and we are asked to determine if it converges or diverges. And in this case, we can see it converges, and even to what value. So just as a reminder, you could have seen this by saying we have a geometric series, which we talked about last time. And the geometric series, the very first term in the series, so the a value, the first term, or a sub 1, is 6/10, and that the r value that we multiply by each time for the geometric series is 1/10. So this is a situation where we have a geometric series, because you're multiplying by 1/10 each time to get the next term in the series. The first term is 6/10. So we have a formula. The sum for a geometric series with the r value of less than 1 is the first term divided by 1 minus r. So in this case, this would be 6/10 divided by 1 minus 1/10. So that's 6/10 divided by 9/10, because 1 minus 1/10 is 9/10, which means the same as time 10/9 if we flip it and multiply, which is 6/9, which simplifies to 2/3. So if I didn't just recognize that a repeating 0.6 decimal is 2/3, then instead, by recognizing that this is a geometric series and r is less than 1, then I could evaluate it with the formula for a geometric series, knowing the first term, and I would also get the same result. Okay, so what are we considering in this first example? This is a geometric series, and we were able to conclude that it converges. In this case, because it's a nice geometric series, we were able to determine what it converges to. But definitely, at the very least, we are able to determine that it converges. Questions about this first example? Okay, so now let's consider another example. And this is all warm up for getting ready for tests, things like that. So as another example, consider this series. The series of 1/k. So again, what do these terms look like? So if I plug in a 1, I get 1/1, which is 1. If I plug in a 2, I get 1/2. And then I get 1/3. And I get 1/4, etc. So this is an infinite series. And we can ask ourselves, does it converge or does it diverge? And you could imagine partial sums, like adding up as you go. I'm starting with a 1, then I get 1.5. Then if I add a third to that, that's like 1 5/6, which is a little bit less than 2. But if I add a fourth, I get a little bit more than 2. But I am adding less and less every time. So it does seem to be that the amount I'm adding is diminishing. So maybe it settles in on a value, or maybe it doesn't. But this is a very, very important series. So we're actually going to give it a name. As we discuss it, as an example, we're going to give this a name. So this is called the harmonic series. And that's just the series as k goes from 1 over infinity of 1 over k. 1, 1/2, 1/3, 1/4, 1/5, add it all up. Okay. So there's a couple of ways to look at trying to determine whether this converges or diverges. The book uses this as an example and looks at it graphically, looking at the partial sums. It also does it numerically by plugging in bigger and bigger values of k. So what I'm going to give you now, just to highlight all of that, and I think they might give you this too, is an analytical argument. So big picture first, what are we doing? We're looking at an infinite series, and we're going to try to see if it converges to a value of some sort or diverges. So I'm going to write it out a little bit more here. So I have 1 plus 1/2, 1/3, 1/4, 5th, 6th, 7th, 1/8, 9th, 10th, and it just keeps going until we're all dead. Okay, so this is the harmonic series. Nice little pattern. So let's consider the following. So I'm going to look at adding some of these up in particular groups. So this is all addition. We can kind of add up in any order we want. So if I look at these two numbers together, what I'm going to point out that the result of 1/3 plus 1/4 is more than 1/4 plus 1/4. Because 1/3 is a larger number than 1/4 is. The bigger the denominator, if everything else is held constant, the smaller the value you get for the fraction. So the sum of those two numbers is more than 1/4. So now in a similar way, I'm going to look at the next 4 numbers as a group. So the first 3 of these, 1/5, 1/6, 1/7, those are all more than the last one, which is 1/8. So these 4 as a total will be more than 1/8 added up 4 times, because the first 3 of the fractions are actually more than 1/8. So 1/4 plus 1/4 is 2/4, which is 1/2. And 4 1/8 added together is 4/8, which is also 1/2. Then I could do this again by going out for the next, not 4 terms, but if I double the number of terms I go out, I'm going to get to the 16th 1 over 16. So that would be more, and I would do this for 8 terms, the 9, 10, 11, 12, 13, 14, 15, 16th terms, would be more than 8 times 1/16th. Because each of those, except the very last one, are more than a 16th, and there's 8 of them. Just like there was 4/8 here, 2/4, 4/8, 8/16, which is also, of course, 1/2. And I could just keep doing this in the harmonic series. So in the harmonic series, I start with a 1, then I add a 1/2, then I add a couple of numbers that end up more than a 1/2, then I add 4 numbers that are more than a 1/2, then I add 8 numbers that are more than a 1/2, then I could go further down and add the next 16 numbers, which would be more than a 1/2, et cetera, et cetera, et cetera. Sorry. So what goes on here is that basically by going further and further out in the series, I can always get the next big batch of numbers that will add up for more than a 1/2. And I can do this forever. So I can keep adding a half, a half, a half, a half, a half as many times as I want, and that will eventually get larger than any number I can think of. If I want to get larger than 1,000, then I just add 2,000 1/2. If I want to get larger than 1,000,000, then I'm going to add up 2,000,000 1/2 plus the 1 in the beginning, and I get 1,000,001. And I could just keep doing that forever. So ultimately, this is an argument that says that the total goes to infinity and diverges. And so our conclusion is that the harmonic series, the series of 1 over k, as k goes to infinity, diverges. Questions, comments, discussions about that? Okay, so let's consider what we just looked at, because this is going to be the position that we're in basically for the rest of the chapter, that you are considering a series and asking yourself if it converges or diverges. We're looking at a series and asking, does it converge or diverge? So we had 2 examples. I have my first example here of 6 times 10 to the minus k, which ended up is just a bunch of 0.6s on the decimal. And we found that that converges, and even found the value that it converged to, which is 2/3. Then we looked at another infinite series, the harmonic series, 1 plus 1/2 plus 1/4 plus 1/4, etc. And we concluded analytically, with a little bit of justification, that this diverges because the grand total ends up heading off toward infinity eventually. So what we are now going to do is we're going to put together a series of tests. When you're looking at a series and you're trying to ask yourself, does it converge or does it diverge, and whether I could use a test to help draw that conclusion. So the very first test is Theorem 8.8 on page 627. It's called the Divergence Test. So the Divergence Test says the following. If you have some infinite series of a sub k's and it converges, then the limit as k tends to infinity of a sub k must be 0. So equivalently, that means that if the limit of the a sub k's is not 0, that it must diverge. Since every convergent series, the limit of the terms must be going to 0, that means that you can see if a test diverges if that's not the case. So this kind of makes sense, right? So for example, let's take a super simple limit. Let's say I had the limit, simple series. Let's say I had the series as k goes from 1 to infinity, and let's just say it's like a constant, 0.1. So what does this look like? This is 0.1 plus 0.1 plus 0.1, etc. So in this case, you could sort of imagine perhaps that if I just keep adding a 10th, eventually I'll get bigger than any number imaginable. If I add 10 of them, I get 1. If I add 100 of them, I get 10, etc. If I add 10 million of them, I get a million. So we could see that this diverges because of that argument, but notice that I can take the limit as k goes to infinity of the constant 0.1, and I get 0.1. So the divergence test tells me that since this is not equal to 0, and I know that for any convergent series, the limit must be 0, that if the limit is not 0, it therefore diverges. So the divergence test is only a test for divergence. It never allows us to conclude whether something converges. So just to be clear, if the limit of k going to infinity of the a sub k's is equal to 0, we still don't know if it converges or diverges. And why can I make that clear? Well, because the first two examples we looked at were both like that. The very first example we looked at, six times 10 to the minus k, the limit of that is 0, and the series converged. But then when we looked at the harmonic series, the limit of the terms of a harmonic series are also 0, but we found that the harmonic series diverged. So if you're trying to use the divergence test and you take the limit as k goes to infinity of the terms and you don't get a 0, then the divergence test tells you conclusively that series must diverge. However, if you're trying to use the divergence test and you take the limit as k goes to infinity of the terms and you do get a 0, then the test doesn't give you any information. You don't know if it converges or diverges because both are still possible if the terms go to 0. You have to do something else. So let's see an example perhaps that they give us. So maybe we'll look at example 1 on page 628. So let's take a look at part B, for example. Part B has summation as k goes from 1 to infinity of 1 plus 3 to the k over 2 to the k. So we could sort of say, well, what is this? What looks like is going on here? So for example, I'm running out of space here. Can I go down? No. Okay, that's what my trouble is. All right. So what's going on with these terms? As k is 1, 2, 3, 4, 5, we could be trying to figure out what's going on. So for example, if k is a 1, I have 4 over 2, which is 2. If k is a 2, I have 3 to the second is 9, plus 1 is 10 fourths, which is 5 halves. If k is a 3, then I have 3 to the third is 28 over 8, which is what, like 14 7 halves. So what we may be able to see here is that as k gets bigger and bigger, the numbers are sort of, they went up to 2.5 here, but then you have 4. They seem to be getting larger, not smaller. It certainly looks like these terms aren't going to 0. And maybe you could also convince yourselves of that by taking note of the fact that the 1 becomes insignificant as these become large, and this basically then just looks like 3 over 2 to the k. And if you have a number bigger than 1 and you raise that to the k, that heads off to infinity. We looked at that with a geometric sequence. But nonetheless, we could also do some algebraic manipulation, and I'll model some of that. The book kind of splits this into two and says you could consider this as the series of 1 over 2 to the k plus the series of 3 over 2 all to the k, because I could just divide the 2 into each of these two terms in the top, and then I would get these two things. And then the second part here is a geometric series. They both are, but this is a geometric series that goes off to infinity. And therefore, the sum of these two things must diverge. So you could see that by simply taking the limit of the kth term, and then you would see that the limit is 3/2, because if I take the limit, this goes to 0 and this goes to 3/2 of the terms getting to a bigger and bigger power. As I said, that goes to infinity. So since the term itself goes to infinity, the divergence test says that that must diverge. Questions, comments, or discussion about this example 1 for looking at the use of the divergence test? So this is our first test, and basically it just says that if I have an infinite list of numbers that I'm adding up, if they don't go to 0 as I'm adding them along the way, even if they're 1/10 or something like that, if those terms aren't shrinking away to nothing, it has to diverge. So I'm going to clear this. So we have a test now called the divergence test, and it does only give us a way to look for divergence, not convergence. But if it tells you it diverges, then we know that. Okay. So after looking at the divergence test, the book spends about a page and a half introducing the harmonic series, which I've already introduced. But they look at it, as I mentioned before, they look at it numerically, they look at it graphically, but then they give you a theorem out of it. So just to take note, Theorem 8.9 on page 630. Says that the harmonic series, which is the summation of 1 over k, diverges. So I've mentioned this before, that this thing's going to be very important for us. We're going to regularly be looking at the harmonic series in our subsequent work. And so it's good to think about, good to try to recognize it. And we literally have a theorem telling us that one specific series diverges, because it ends up being important. And so I gave an analytical argument. However, they also then introduce another test we could use. So let's look at our second test here. This is Theorem 8.10. On the same page. So this is called the integral test. And then pretty quickly we will add that up here so that we also have the integral test. I'm going to have to erase all this in a bit, but I'll just put it up here to sort of say we're accumulating tests here. So what does the integral test say? Suppose f is a continuous decreasing positive, my pen is not writing very nicely, function for x greater than or equal to 1. And let a sub k, meaning the terms of some sequence, be equal to f of k. And this will again be k being a natural number. Then the infinite series, as k goes from 1 to infinity of the a sub k's, and the improper integral from 1 to infinity, chapter 8, of the function both converge or both diverge. So what does this mean? So this means that if you have a series where the terms of the series can be viewed as values of a continuous function, and we know the improper integral of that continuous function can be seen to converge or diverge, then the series must also converge or diverge just as the improper integral does. And so if we, for example, were looking at the harmonic series, because we've done that already, like let's say we were looking at the harmonic series, which is 1 over k. So this would compare to the integral from 1 to infinity of the function version of this expression, which is 1 over x dx. And that's one of the ones we did in chapter 8. In fact, that was a crucial one that I said we should look at very carefully, because later that's going to translate to the harmonic series now. So again, this was that function 1 over x, where it goes through the point 1, 1, and then we could consider the area under the curve to the right of a 1 in that tail. So that's what this improper integral represents. And that when we did this improper integral, we took the limit as b went to infinity of the integral from 1 to b of 1 over x dx. And we got a natural log, and that ended up just being the limit as b goes to infinity of the natural log of b, which diverged. So we already concluded in chapter 8 that this improper integral was divergent. But now we can take that divergence and translate that to say that the harmonic series also diverges, because that's the same formula for the series as it is for the function over here. And we can do that in proper integral. So that basically what the integral test allows us to do is to say, okay, if you are looking at a series, and if you look at the formula for the terms of the series, ask yourself, if that formula was a positive continuous function, would I be able to determine whether the improper integral for that function converged or diverged? Because the series will do the same thing that the improper integral does. They'll either both converge or they'll both diverge. So it allows you to basically say, hey, if I took the integral of that formula, would I be able to look at that improper integral and determine what's going on? Questions, comments, discussions about what the integral test says?
Can you repeat that last part one more time?
Yeah, so the idea of how to apply the test is that you imagine you're looking at a series. And you're trying to I need to figure out if this converges or diverges. Well, the series will typically be presented with some sort of a formula for the kth term, right? Like
Right.
1 over k. So you say, all right, well, I'm looking at this. So ask yourself, what if that wasn't a k? What if that was an x? And I had some function 1 over x. Could I determine whether the improper integral from 1 to infinity of that function converged or diverged? That would be a chapter 8 problem. If this produced a chapter 8 problem that we could do, like the one that we just did here as an example from before, then whatever you conclude about converging or diverging for that improper integral directly also is true about the series converging or diverging. So it allows you to draw a conclusion about convergence or divergence based on looking at a chapter 8 integral problem instead of looking at the series directly. Does that answer your question?
Yeah.
All right, well, let's do another example. I'll do one maybe that they do for you here. Yeah, let's look at example 2 on page 631. So it says, determine whether the following series converges. So you're looking at a series. And just to highlight what's going on, we have converge or diverge. That's the question that we're trying to answer. And this is going to be our predicament for a lot of the problems. And the series we're looking at in this case is k divided by k squared plus 1. So we're literally just looking at this and saying, does this converge or does this diverge? So what the convergence test allows us to consider, so you basically say, could I do the integral from 1 to infinity of x over x squared plus 1 dx? Or at least could I determine whether that converges or diverges? So if you were looking at this not as a series problem, but as an integral problem where you're trying to find an antiderivative, do we think we could come up with the antiderivative or the integral for x over x squared plus 1? What do you guys think? Chapter 7. Okay, well, if people are struggling, maybe we want to review that. But basically, I would recommend that you note that if you look at this, you could think that the numerator of the fraction is just a multiple of the denominator's derivative. So we could do this with a u sub. So since we can do this integral, then when we get convergence or divergence of that, we can extend that to convergence or divergence of the series. So to do that, I would say, all right, I need to take the limit as b tends to infinity of the integral from 1 to b of x over x squared plus 1 dx. And then in order to do that, I would use a u substitution where I let u equal to x squared plus 1. So then du is equal to 2x dx, or dx is equal to du divided by 2x. So then that allows me to do a substitution. So I do the limit as b goes to infinity. And then I have x in the top and u in the bottom. And then dx gets replaced with du over 2x. So then I would also need to change my limits of integration. So for example, when x was equal to 1, then I would get 1 squared plus 1 is 2. So my new limit of integration would be a 2. And when x is equal to b, then I would get for u b squared plus 1. That'd be my new upper limit of integration. And of course, these x's cancel out. I wrote dx instead of 2x. Let me fix that. Because I'm using the substitution for dx equals du over 2x. So these x's cancel out. So then that gives me the limit as b tends to infinity of the integral from 2 to b squared plus 1 of 1 over u du. So that's the limit as b tends to infinity. So the antiderivative of 1 over u du is ln of absolute value of u, but u is going from 2 to b squared plus 1. That's always positive, so I can just do ln of u evaluated from 2 to b squared plus 1. So, oh yeah, I forgot the 1/2. Thank you, Wenzel. So the 1/2 is a constant that can be pulled out of the whole thing. Let's say this step I pulled it out to here, and then for this step I pulled it out to here, because constants can be pulled out of integrals as well as limits. So then this would be 1/2 the limit as b tends to infinity of the natural log of b squared plus 1 minus the natural log of 2. So natural log of 2 is just a constant, but as b goes to infinity, b squared plus 1 is going toward infinity. And as we saw even in the very earlier example, if I take the limit as b goes to infinity and ln, the thing inside, is going to infinity, then this whole thing goes to infinity as well. So that means that this limit diverges, which means that this integral diverges. So therefore, by the integral test, this series diverges. Questions, comments, discussion about that example of using the integral test to do a problem? So in this case, we could say, okay, this diverges, so I'm choosing D, diverges. So again, what was our situation? We were looking at a series, and we were trying to figure out if it converged or diverged. And what the integral test allowed us to do as a tool is say, well, if I can do the improper integral, could I do the improper integral from 1 to infinity of this expression as a function in x instead of as a series term in k? And if I think I could do that integral, at least enough to determine whether it converges or diverges, then I'll be able to use that result for my series as well. Questions, comments, discussions about the integral test for convergence or divergence? Okay, so let's give it a fresh page. So now we have a couple of tests. We have the divergence test. And we have the integral test. So now we're going to look at Theorem 811 on page 632, which is the P-series test. So it states as follows. The P-series, which is the series as k goes from 1 to infinity of 1 over k to the p. So this is called the P-series. And we've looked at this already in terms of even improper integrals. But the statement says that the P-series, this P-series converges for p bigger than 1 and diverges for p less than or equal to 1. So let's note P is for power. This is a power series basically. You have just a simple power in the bottom of the k value. And so this goes back to the P series that we had for improper integrals where we integrated, and that's where we got the 1 over x is the borderline for divergence, and that if you have 1 over x squared or any other bigger power, you get convergence. So this is saying the same thing that we said about improper integrals of a P series back in chapter 7. Now, we could immediately apply this, for example, as a way to also do the harmonic series. Now, we've already looked at the harmonic series lots of ways. The integral test would do the harmonic series, but the harmonic series is an example. So note, let's do this. So take note, the series k goes from 1 to infinity of 1 over k, which is, again, the harmonic series, is a P series. With P being equal to 1. Therefore, it diverges. Therefore, it diverges by the P series test. Because the test says that if you have a P series, just look at the value P, and if it's less than or equal to 1, it diverges. If it's greater than 1, it converges. So this is a P series where the P value is equal to 1, and therefore, by the P series test, it diverges. So we already know the harmonic series diverges, but this is another way you can see that it fits as a P series test and that we can confirm that with the P series test. And we keep looking at the harmonic series because it is a borderline case. It's right on the edge. So that's why we want to think about that. Okay, so now let's look at an example that they give to help us do this. So let's look at example 3 on page 633. And maybe we will look at B. So this gives us a series as k goes from 1 to infinity of 1 over, and it has the fourth root of k to the third. So again, we would be looking at a series, and the problem says determine whether the following series converges or diverges. Converge or diverge. So C or D. More and more, you're going to have this exact same instruction. Just determine whether the series converges or diverges. You just have to choose between the two. And again, that means that if it does converge, they're not even asking for the value. They're just asking, does it converge or diverge? So this example is here because this could be rewritten so that it can be more easily seen to be an example of a p-series, because the fourth root can be thought of as a 1/4 power, and the k to the third is also a power, so this can be written all together as k to the 3/4. So Wenzel says, is this preferred over the divergence test? Not sure. Are you talking about integral? So just to answer Wenzel's question, I'm not sure if I'm too late to the game. The integral, okay. So the divergence test is always the first test to think of because it's often so easy if it works. Because you just take the limit of the terms, and if they don't go to 0, you just immediately say, oh, well, it diverges, and I don't need to think about anything else. But the problem will be, that's like a quick default to always keep in mind. The problem is that most of the things we're going to look at, the terms themselves are going to 0, and therefore we don't know if it converges or diverges. Then we start thinking about integral, p-series, etc. So for example, in this case, you just have k in the bottom of a fraction. So if k is in the bottom of the fraction and k is getting bigger and bigger and bigger and bigger, then the fraction's going to 0, and the divergence test fails to tell us whether this converges or diverges. Remember, the convergence test is a completely one-sided test. Sorry, the divergence test is a completely one-sided test. It either gives divergence or it gives nothing. And it does it in a very simple way that often doesn't apply. Like in this case, you could not get anything from the divergence test because the limit of the terms is 0, and the divergence test therefore has no idea whether it converges or diverges. Does that answer your question, Wenzel? Yeah. Okay, but instead you could say, hey, this is a p-series. So we can say p-series with p equal to 3/4. So if p is equal to 3/4, does this diverge or converge? Correct, so we can see it therefore diverges because p is less than 1. And if p is less than or equal to 1, then we just immediately say, okay, it diverges. So that gives us our answer. So that's an example of using the p-series to do a problem, and they'll give you some other ones as well. So questions about that? Okay, so now there's going to be a theorem 812, and I'm basically going to skip it. I'm going to suggest you guys look at that if you need to. So I'm going to write here, students look over theorem 8.12 if needed to do an online problem. And it'll be very clear if that's the case, but it's really not worth our time and effort in our group setting face-to-face. So if you get stuck with it or you have questions about it, it's about estimating the value of a series. And the reality is that if we are able to determine that a series converges, we know that it converges, and we want to estimate its value, well, if you know it converges, then you can do that numerically much more in a straightforward way. You could just put in very big values of k and see what it settles on, or something like that. There's definitely ways to go about that. But I want to focus our work on developing the skill of using tests to determine if series converge or diverge, because that's like everything we want to get out of chapters 8 and 9 in particular. Okay, so let's instead take a look at another theorem about how to manipulate stuff. So theorem 813 on page 636. And this is properties of convergent series. So looking at series, infinite series, we end up with a limit basically as k goes to infinity of something, and we have a series. So properties of limits and properties of series can kind of be combined together to give us a couple of ways to manipulate when we're working with series. And so they basically, this is kind of like limit laws or properties of limits, but there's just a couple of them, as well as properties of series, which we did back in chapter 8 a little bit. So we're going to say that you have an infinite series of a sub k's that converge to the value of a. You have an infinite series of b sub k's that converge to a value b, and c, and little c is a constant. Then we can do a couple of manipulations. So the first one will hopefully look familiar. Then the summation of c times a sub k. So that's where we're taking each term in the a series and multiplying it by the constant c. We know the a terms add up to capital A. So if we multiply each by c, then the result you get is c times the total of the a's. So this is basically that if I have a c, I could pull that outside. It's basically saying if I have a constant multiplier, I could pull that outside, which we already know we can do that, but that's true with finite series, but that's true with infinite series as well. As long as it converges, then you can multiply by the constant and focus on getting the series of the a sub k's without the same number outside each time. So that probably looks familiar as a manipulation, pulling out a constant. And then we also have, if I have a summation of the a terms plus the b terms, well, then I can split up the summation as we've done before. I can do the sum of each of those separately, and I know the a's go to a and the b's go to b, so this would just give me a plus b. And this would be true also if we were doing subtraction. Oops. A sub k. And this would be true also if we were doing subtraction of the two. So these first two, I think, look pretty familiar, but the third one is a little bit more interesting. So the third one we probably want to look at and at least try to understand it. So basically the first one says if you're multiplying each term by a constant, you can pull that out of the series. And if you have terms that are created by adding up individual series terms, then you can do those separately when you're considering a convergent series. But the last one says, if m, some number m, is a positive integer, then the summation as k goes from 1 to infinity of some series a sub k that converges, and the summation as k goes from m to infinity of the a sub k's converge or diverge together. Meaning they either both converge or they both diverge. So what is this saying? So this basically says, like, we know, here's an example. We know the summation as k goes from 1 to infinity of 1 over k diverges. Again, this is the harmonic series. So then the summation as k goes from, how about 1 million to infinity of 1 over k also diverges. So basically what this says is that if a series diverges, it doesn't matter where you start counting, because it's going to diverge or converge. That is completely determined by what happens as you go to infinity, not what happens in the first finite number of terms. So hopefully this can kind of make sense without too much work, because the basic idea is that how is it going to diverge? It's either never going to settle on a value or it's going to head off toward infinity. Well, what happens in the first million terms has nothing to do with that. Right? The sum of the first million terms of any series is just a number. And so if I have some number in the first million terms, and then after that, it settles on a 5, well, then I have a convergent series that settles on 5 plus the first million terms total, whatever that is. It's just a number. But if I have some series that in the end heads off to infinity, well, it doesn't matter what it does in the first million terms. If the end heads off to infinity, then that's going to happen whether I add some number in the beginning or even subtract some number if I had some negative number in the front. So a finite number of terms in a series has no impact on its divergence or its convergence. Only what it does in the life tail as you head off toward infinity, only what that pattern does. So basically this part 3 of the properties of convergent series is telling you that whenever you're considering whether a series is convergent or divergent, not worrying about if it converges to a particular value, but just simply converge or diverge, well, then it doesn't matter where you start counting in the series. That you can, if you wanted, like if the first few terms were confusing, you could say, well, I'm just going to start k at 1,000 and then see what happens after that. If that's beneficial to you, you can do that. Questions, comments, discussions about that? Okay, so they have a problem, I think, that we may look as an example. Of course, we could look at lots, but let me take this example away for part 3. And let's look at another one they'd like us to do. So how about example 5? 637. So it says evaluate the infinite series. And it has the series as k goes from 1 to infinity of 5 times 2/3 to the k, yeah, minus 2 to the k minus 1 over 7 to the k. Okay, so this is the statement of the problem. We're supposed to evaluate these series. So we can assume that therefore it converges because we're supposed to figure out the value of it. And it looks kind of messy. So it would be nice if we had some manipulative abilities, some properties of convergent series that would allow me to simplify what I have here. So for example, I can see there's like a constant multiple in here, and that I'd like to pull out. And then I also have like a difference here, and I'd like to sort of distribute the summation across the difference as well. So using properties 1 and 2 of the Theorem 813 that we just looked at, that means I could rewrite this as 5 times the series as k, okay, as k goes from 1 to infinity of 2/3 to the k minus the series as k goes from 1 to infinity of 2 to the k minus 1. Yep. Divided by 7 to the k. So this helps us because we can focus the series just on these terms with the k parts in them, not worry about the constant, not worry about the difference. So then we could do this problem. Well, this first one, for example, the nice part would be to recognize that this is a geometric series. If k is a 1, I get 2/3. So that means the first term in my geometric series is 2/3. And what I'm multiplying by each time, since k is an exponent on the 2/3, getting bigger and bigger, is I'm multiplying each time by another 2/3. So now what's going on in the one on the right over here? Well, you can see here also that the top, you just have an increasing power of 2. And the bottom, you just have an increasing power of 7. That means each time I move on to the next term, I get multiplied by 2 on the top and 7 on the bottom. So that means the whole thing is just multiplied by 2/7. So perhaps we can recognize that this part here is also a geometric series, where the first term, so when k is a 1, I get 2 to the 0, which is 1 over 7 to the 1, which is 7th. So the first term is 1/7. And then each time I go over from there, as k gets 1 bigger, I multiply by another 2 on the top and a 7 on the bottom. So r is 2/7. So we can evaluate both of these pieces using the fact that they're geometric series, and we have a formula for the sum of an infinite geometric series as long as the r value is less than 1, which it is. So the formula for this is then that the sum would be the a value divided by 1 minus the r value. And that's true for both of these. A value divided by 1 minus the R value. Okay, so what do I get? 5 times, so 2/3, 1 minus 2/3 is 1/3. So that's 2/3 dividing by 1/3 is the same as multiplying by 3/1. And then there's a minus in the middle. And then over here, I would have 1/7. And then 1 minus, I said 2/7, but I wrote 2/5 over here. So let's fix that. Then I would have 1/7. 1 minus 2/7 is 7/7 minus 2/7, which is 5/7. So to divide by 5/7 is to multiply by 7/5. So there's a little bit of arithmetic there, but then these cancel out. And you get 5 times 2 minus 1/5, which is 10 minus a fifth, which is like 9 4/5 as a mixed numeral. So it said to evaluate the series, and by using the properties of convergence series, we were able to break this into simpler things to be evaluated, recognize that we have a couple of geometric series which can be totaled up with their formula, and got this result. So that's an example of using properties of convergent series, which is Theorem 8.13. Questions, comments, or discussions about any of that? Okay, so let's just review the most important things. We got an ability to manipulate, but the most important things in this section was that we had 3 tests: the integral test, the divergence test, and the P-series test. And then in 8.5, we're going to add several more tests to finish up with our collection of tools for determining whether series converge or diverge. So this brings us to the